Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Transducers, a Gentle Introduction. As always, please be an active listener as you watch this video. By way of introduction, transducers are a very serious topic. It's the primal ultrasound tool. It's where you come into contact with your client. There's tons of math involved, there's tons of science involved, and there's tons of engineering that is involved in these transducer tools. And they have a noble history with some very heavy-duty history of science people involved as well. So here we go. So a transducer is actually any device that converts one form of energy into another. And there's all kinds of transducers, and the ultrasound transducers transmit, and so it goes from electrical signals to acoustic signals. And when it's receiving, it is going from acoustical signals to electrical signals. During transmission, the electrical energy from the system is converted into sound. During reception, the reflected pulse is converted into electricity. Now, the way this works is we have the piezoelectric effect, which describes the property of certain materials to create a voltage when they are mechanically deformed or when pressure is applied to them. So we apply electricity to these materials, they vibrate, and that causes sound waves that go into the body. When it comes back, what happens is the piezoelectric materials change shape when the voltage is applied to them, and that is a process called the reverse piezoelectric effect. So this is the property that creates a voltage when they're mechanically deformed and pressure is applied, and here that's the reverse effect. So together they is the transducer. Now, the materials which convert sound into electricity and vice versa are called piezoelectric or ferro, standing for iron electric. Now, some of these materials, quartz and tourmaline crystals, are found in nature, but those commonly used in clinical transducers, where you're going to be doing most of your work, are lead, zirconate, titanate, and since lead's abbreviation is P, actually it's PB, then that's P, Z, and T is the way that's summarized. And these are synthetic or man-made materials, and they're largely considered ceramics. So PZT then is an ultrasound transducer, and it's also known as ceramic, the active element, or it could be a crystal. Modern transducers are very elaborate. They can do a lot of different things, but most of them share the design characteristics with a simple, single crystal, unfocused probe. So, without getting into these advanced topics, let's just look at the design of these simple probes to understand basically the transducer characteristics and how it functions. So there are 7 parts. The case, which is the outer surface, the electrical shield, and the electrical shield keeps electrical signals from coming in and the electrical signals inside from going out. The acoustic insulator, which is here, and that is again keeps sound from going in and going out. The active element, or the PCT, a variable that is here, and you have a wire taking this back to the computer system, and you have matching layer that is here, and the matching layer does some impedance matching actually between these layers and the matching layer, and you further apply gel on this. And there's also a thing called the backing material that is sometimes here, depends on what the transducer is doing, but it's also called the dampening element because this actually dampens the signal and makes it appropriate for clinical applications. So that's what it is, and here's more words talking about what each of those layers does. We'll talk about some of these things. The matching layer and gel increase the efficiency of sound transfer between the transducers P, ZT, and the skin. So increasing order of impedance, and remember we talked about impedance, the PCT is bigger than the matching layer, is bigger than the gel, is bigger than the skin, and then you go into the soft tissue. So this is the order of the things, and realize that differences in impedance result in reflections at the boundaries. So larger reflections occur with greater impedance differences. So what you're going to do is you're going to go through and take really strong signals and make them more appropriate so you can get maximum transfer of the energy. The thickness of a matching layer is 1/4 of the wavelength of sound in the matching layer. And the thickness of the active element, that is the PZT element itself, the thickness is 1/2 the wavelength of sound. And so those are things that sometimes could be asked on certification exams. The backing material plays an essential role, and what it does is it decreases sensitivity, provides a wider bandwidth, and a lower quality factor. And the reason you do this is that, and what it does is it has a high degree of sound absorption, and this helps with the acoustic impedance matching so you can get a quality signal. Okay, so we'll talk about what are the consequences of decreased sensitivity. The backing material not only reduces active element vibration during transmission, but also reduces vibration during reception. Now this is an undesirable characteristic because transducers are less responsive to tiny reflected sounds. But for gross kinds of ultrasound exams, this is useful. If you have a therapeutic ultrasound, you might want to have less backing material or maybe no backing material at all. And decreased sensitivity means that during the reception, transducers with damping material are less able to convert low-level sound reflections into meaningful electrical signals. Now, when the backing material is applied to a vibrating object, the PZT crystals, for example, of an imaging transducer, the crystal is prohibited from vibrating freely. And so it restricts what happens, and that means that you basically get a short duration click rather than a steady long tone. And so it's a click. Although the sound click, although short, contains sound at many different frequencies, and they're spread over. So you see, you can be spread over a lot of frequencies and having a wide bandwidth, or you can be very focused in a narrow bandwidth here. And you can see that the energies are different associated with these. There's more energy associated with a narrow bandwidth, and so the imaging tends to have a wider bandwidth, and so there's a range. Imaging probes produce pulses that are identified as wide bandwidth or broadband. Other probes, such as those used in therapeutic ultrasound or in continuous wave Doppler, do not use backing material and produce narrow bandwidth pulses, and you saw that picture up here. And just as an example, a transducer with a 3 megahertz main frequency produces a sound pulse that contains frequencies ranging from 1 megahertz up to 5 megahertz. The bandwidth or range of frequencies of the pulse then is 5 megahertz minus 1 megahertz, or 4 megahertz. As a general rule, long duration events are narrow bandwidth, whereas short duration events are wide bandwidth. There's also a term that is used in your trade called quality factor. The quality factor is the main frequency divided by the bandwidth. Wide bandwidth probes, that means the denominator gets bigger, have low Q, whereas narrow bandwidth probes have high Q factor. So imaging probes tend to have low Q, and therapeutic or continuous wave Dopplers don't contain a background at all, and that means they are high Q. And so you want to remember the relationship between damping and Q factor, knowing that the Q is directly related to the pulse length. So a shorter dampened pulse has a lower Q factor. A longer undampened pulse has a higher Q factor. And as just a numerical calculation, a 3 megahertz transducer with a bandwidth of 4 megahertz has a Q factor of 3 over 4, or 0.75. Let's talk more about piezoelectric materials. So the properties of lead, zirconate, titanate, PZT do not occur spontaneously. Rather, these properties are created by exposing them to a strong electric field, and this is called polarization. There is a temperature called the Curie temperature, and this is the Curie temperature, or Curie point. It's named after the scientist who invented this. So piezoelectric properties can be destroyed by exposing it to a high temperature, and that's called depolarization, and the PZT is said to be depolarized. So you want to stay away from these temperatures. And you do have to maintain them, and there are two things you do with medical instruments. Sometimes you sterilize them, you do disinfectants with others. Since the ultrasound transducers rarely penetrate mucous membranes, they're less likely to transmit infection, and so they only require disinfection. And those that are endocavitary are even less critical, since they are routinely covered with a single disposable use barrier. So anyway, sanitation is important, and the things you're reusing can be disinfected with some of these cold germicides. Let's go through some questions that are here, and these questions are intended to mirror those that are on certification exams. So you are given 5 substances: backing material, PZT, matching layer, gel, and skin, and the impedances have been identified. Unfortunately, the labels identifying the impedance of each have fallen off, so the labels are impedance of 0.8 megarails, 1.9 megarails, 1.6 megarails, 2.0 megarails, and 1.0 megarails. If the impedance of the backing material is 1.9, what are the impedances of the other tissue, matching layer, gel, and PZT, and why? And here's what they are. So the PZT is the largest number, matching layer is next, gel is next, and the skin is the lowest of the two. Pulse length is either directly or inversely related to pulse duration. It's directly related to pulse duration. The Q factor is directly or inversely related to bandwidth. It is inversely. Pulse duration is directly or inversely related to bandwidth. It is inversely. Sensitivity of transducers that create short duration pulses is likely to be, say, greater than or less than or equal to that of transducers that create big pulses. The answer is less than. All of the following correctly describe an imaging transducer except, and it's a high sensitivity. True or false? Shorter duration events, such as damped pulses, are more likely to have wide bandwidth. That is true. And what occurs when a PZT crystal temperature elevated above the Curie point? And it is depolarization. And the properties are lost, and the transducer is ruined. So you want to avoid that. Now, transducers can either be continuous wave transducers, or they can be pulsed wave transducers. And so here the electrical frequency is equal to the acoustic frequency. So if it's 6 megahertz electrical signal, then the acoustic frequency is also 6 megahertz. But a pulse ultrasound system that creates a short duration wave is sent as a spike. So you have kind of on and off signals that are sent as it goes along, and this is more what you're going to be using when you're doing imaging studies. And the characteristic of the active element here is with a pulsed wave transducer, the speed of sound in the PZT and the thickness of the PZT both have an influence. So how does the speed of sound in the PZT affect frequency? Well, the speed of the sound in PZT, which is a solid, and the frequencies of sound are directly related. So the higher you make the speed here, the higher the frequency you're sending. Now the speed of sound in most of these ranges, again, they are higher. These are 4 to 6 millimeters per microsecond, and that's the same thing as, well, 6 would be 4 times 1.5, which is the speed in soft tissue. So this is about 4 times greater or than the speed of sound in soft tissue. And this is a value that's characteristic of each piece of the PZT and cannot be changed. So you want to remember that the relationship between speed of sound in the PZT and the frequency, and they are directly related. How does the thickness of the PZT affect the frequency? Well, the PZT frequency and thickness are inversely related. So that means that thinner active elements create pulses of higher frequency and shorter wavelength cycles. Thicker active elements create pulses with lower frequency and longer wavelengths. Again, that's something that often is on certification exams. The thickness of the PZT crystal is equal to 1/2 the wavelength of sound in the PZT. Again, some summary questions that we'll go through. The acoustic impedance of the matching layer is approximately the same as the acoustic impedance of the skin. That's false. Imaging transducers are usually of high rather than low bandwidth. That's true. A very high Q factor transducer is used more often in diagnostic imaging than a low Q factor. That's false. Imaging transducers are low Q factor. A pulse with a long pulse duration is likely to have a narrow bandwidth. That's true. The damping material in a transducer increases the sensitivity. That's false. The damping material in a transducer increases the pulse length. That's also false. The damping material in a transducer decreases the pulse duration. That is true. The damping material in a transducer improves the system's lateral resolution. That is false. The damping material is in a transducer improves the longitudinal resolution. That is true. The damping material in a transducer decreases the bandwidth. That is false. Damping material increases the bandwidth. The damping material in a transducer increases the quality factor. True. And if the frequency of the electrical excitation voltage of a pulsed wave transducer is 6 megahertz, then the operating frequency of the transducer is 6 megahertz. That's false. It would be true if this were a continuous transducer. If the pulse repetition frequency of a transducer is increased, then the frequency of sound produced by the transducer remains the same. That is true. The diameter of the active element of the transducer helps to determine the frequency of the sound that the transducer creates. That's false. The diameter does not determine the frequency of the sound created by the transducer. This is the active element. 15. If the frequency of the electroexcitation voltage of a continuous wave transducer is 6 megahertz, then the operating frequency of the transducer is 6 megahertz. That's true. This is true only for continuous wave transducers. Two piezoelectric crystals are made from the same material. The thicker crystal will make a higher frequency. That's false, because those are inversely proportional. If there are two of these crystals are made with the same material, the thicker crystal will make a continuous wave transducer with a lower frequency. That's false. A continuous wave transducer active element thickness does not determine the beam's frequency. The normal propagation speed in piezoelectric material is about 3 to 5 times greater than in soft tissue. That is true. And the impedance of a transducer active element is 1.9 megarails, and the impedance of the skin is 1.4 megarails. What is an acceptable impedance for the matching layer? And the answer is one that's in between. And this is the only number that's in between the two. It's C. Which of the following crystals will produce sounds with a lower frequency? It's C, thick and with a low speed. Which transducer has a greater Q factor, therapeutic or imaging? Therapeutic. Which type of transducer has a greater bandwidth, continuous or imaging? Imaging have higher bandwidth. Which type of transducer has more backing material? That's definitely imaging. And in a imaging transducer, what is the purpose of the backing material? And what you want to do is to improve the image quality, and that is going to be probably point C. A pulsed wave transducer has a resonant frequency of 5 megahertz. Lowest frequency is 2. So what is the highest frequency 8? What is the bandwidth? Well, the bandwidth is the difference between the two. It's 6 megahertz. For the transducer described in question 25, which was this one, what is the main frequency? The resonant main or central frequency is 5 megahertz. And lastly, for the transducer described again in question 25, what is the Q factor? Well, the Q factor is 5 megahertz divided by 6 megahertz, and so that's going to be 0.8 rounded off, 0.8. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together, and may God bless you all.